is equal to 3 halves times 3 to the power of k minus 1. We've assumed that that's actually true. Okay? And we want to show it true for when we actually add on the next term. So actually, let's add on the next term. The next term in the sequence, yeah, or in the series, the next term, okay, is 3 to the k plus 1. So let's add it onto both sides. So the left-hand side now is 3 plus 3 squared plus 3 cubed plus all the way through to 3k plus 3 to the k plus 1. Okay, we need to show that that's equal to this thing here, okay, 3 over 2 times 3 to the k minus 1. Well, we know that this piece here, okay, this piece here, right here, is actually equal to that from the assumption, but we need to add on to this the 3 to the k plus 1. We're adding on the next term to both sides of what we assume to be true. And we'd like to show that this works out to be, okay, we'd like to show that this works out to be this thing here, okay, which the left hand side actually is. The left hand side is what we want to show to be true, okay. So this left hand side here, the left hand side is 3 plus 3 squared plus 3 cubed plus all the way through to 3k plus 3 to the k plus 1. That is that thing that we need to show. Okay, so it is that, and we need to show, we know that this thing here is definitely equal to this over here, 3 halves times 3 to the k minus 1 plus 3 to the k plus 1. Let's multiply out the brackets here. That gives us 3 times 3 to the k over 2 minus 3 over 2, and I'll multiply out the brackets here, gives me that, plus 3 to the k plus 1. Okay? Well, look at this here. That's actually 3 times 3 to the k is the same as 3 to the k plus 1. So that's 3 to the k plus 1 over 2 minus 3 halves plus 3 to the k plus 1. Okay? What will we do here? Well, let's get the common denominator across here. We're just trying to simplify this algebraically. Okay, so let's just get the common denominator. So let me just do that here. So what we have now is the common denominator is going to be, oops, let's just open this up a little bit. Okay, this term here, we have the common denominator here is of 2, so this must be equal to, it's all over 2. 2 here into the 2 goes once, that gives us 3 to the k plus 1 minus the 3, and don't forget this is over 1, 1's into it goes twice, that gives us plus 2 times 3 to the k plus 1. And look what we have here. Okay, so we have 2 of these things here and we have 1 here, so that gives us 3 of them, so that's equal to 3 times 3 to the k plus 1 minus 3 all over 2. Oh, what's common here? There's a common 3 here and here, so that gives us 3 times 3 to the k plus 1 minus 1 is the top bit all over 2, which is the same as 3 over 2 times 3 to the k plus 1 minus 1. So actually what we've actually shown here is this, okay, is that this thing here all the way down, okay, so actually finally what we have is we have that 3 plus 3 squared plus 3 cubed plus all the way through to 3 to the k plus 1 is actually equal to this thing here, which is exactly what we had to show to be true, which is what we wanted to show to be true. Okay, so once again here we've proved by induction, we've shown that it's true for n is equal to 1. We've assumed it's true for n is equal to k, and we've actually proved it true for n is equal to k plus 1. So if it's true for n is equal to 1, and if it's true for n is equal to k plus 1, well, let k be 1, so it must be true for n is equal to 2, which is 1 plus 1, 2. It must be true, it's now true for n is equal to 2, so it must be true for n is equal to 2 plus 1, which is 3. Now true for n is equal to 3, it must be true for n is equal to 4, n is equal to 5, and so on and so forth. Okay, and that's basically our proof by induction for this particular example. A little bit more complicated than our previous example, okay, but you can see what's going on effectively. We show it's true for n is equal to 1. We assume it's true for n is equal to k. Okay? Then what we do is we see what would we have to show, yeah, for when n is equal to k plus 1. Okay, and then from there we go back to our assumption. We take our assumption and we add on the k plus 1th term to both sides, and we show that from the assumption and after adding on the k plus 1th term that what we get is what we need to show. Okay, which is effectively our proof by induction. Okay, guys, I know that was a little bit fast, yeah, but maybe you can pause as you're going through this particular video and maybe even rewind, yeah. But I suppose at this particular stage, what we have is this was our most recent example, yeah, of proofs by induction. I hope that this was intuitive, and I also, and most importantly, I do actually hope that was actually helpful for you. And thanks for watching. Okay, bye bye, guys.